eventually, it will kill you.
So for our first scenario, we can see that an evil dust cone is growing towards 11. We determined that the height is growing at a rate of 3 meters per second, the radius was growing at a rate of 1/2 meters per second, and the question wants us to find the rate at which the volume is increasing when the height is 12 meters and the radius is 2 meters. So to solve this, we can see that we are given in the problem that radius was 2 meters, height is 12 meters, rate at which height is growing is 3 meters per second, and the rate at which the radius is growing is 1/2 meter per second. So to find the rate at which the volume is increasing, we need to find dv dt. To do that, we're going to look at the original volume equation, and then finding the derivative of that equation. So we'll move our constants to the left, and then use the product rule to find the derivative of those two terms on the right, and that'll give you the equation for dv dt. So then we'll plug in all of our values that were given, and that should give us the solution, which is that the volume of the evil dust cone is increasing at a rate of 37.7 cubic meters per second. Here's a written reflection summarizing the solution process. Feel free to pause it to read in its entirety, but for now I'm going to hand it over to my friend Lucy to tell us about the angle.
Thanks, James. Now let's talk about the angle. The angle is a two-part problem, and in part A, we're trying to find how fast the height of the capsule is increasing, and in part B, we're trying to find the rate at which the angle made by 11's arm in the floor is increasing. To start part A, we must find the length of x, and we can use the Pythagorean theorem to find this. Since we're given that y equals 11 meters and L equals 13 meters, we can plug these values into the equation x squared plus y squared equals L squared, and we'll get that x equals 6.928 meters. Next, we need to find dx dt. For this, we're given that x equals 6.928 meters, y equals 11 meters, L equals 13 meters, and dl dt equals 0.11 meters per second. We can still use the Pythagorean theorem equation, but we need to take the derivative of it using the power rule. Once you do this, you get 2x dx dt plus 2y dy dt equals 2l dl dt. After you plug the given values into the equation, you get that dx dt equals 0.206 meters per second. For part B of the problem, we need to find d theta dt. We're given that x equals 6.928 meters, L equals 13 meters, dx dt equals 0.206 meters per second, and dl dt equals 0.11 meters per second. First, we use the equation sine theta equals x over L. We found the derivative of this equation, which is cosine theta d theta dt equals L times dx dt minus x times dl dt all over L squared. We found the derivative of the equation using the quotient rule and the knowledge that the derivative of sine is cosine. Since cosine of theta equals 11 over 13, we plugged all of the given values into the equation and multiplied by the reciprocal of cosine, which is 13 over 11. We found that d theta dt equals 0.0134 radians per second. Using the answer to part A of the problem, which was 0.206 meters per second, we were able to answer part B of the problem, which was 0.0134 radians per second. Here is a written reflection of the problem. Feel free to pause it and read it in its entirety.